So as we're talking about fluids moving, let's go back to our equation of continuity bottleneck here. So the fluid is moving this way. It's moving from 1 to 2. Let's use a different color here. There we go, from 1 to 2. But fluids flow from high pressure to low pressure. So as we know that it goes this way, it speeds up. But why does it go that way? So over here is high pressure, and over here is low pressure. So it's going to move from high pressure to low pressure. So now that's moving across here. All I'm changing is the kinetic energy. Let's look at a different pipe. So now I have a pipe that have the same area. So by the equation of continuity, the velocity here is equal to the velocity here. Those two velocities are the same. So the kinetic energy is not changing. However, it's going uphill. So what is changing? Well, the potential energy. So here's Y1 and here's Y2. So here, velocity is increasing, but the height is not changing. Here, the velocity is not changing, but the height is increasing. Let's merge them together into a giant space panther. So here we go. Now we have some pipe that starts out large over here at 1. It has some area 1, and it's moving at some velocity 1. And now it's moving up here to, well, it's at some y1, some height above the ground. And now it's moving over here where it has some new velocity because I'm going through a new area, and it's at some new height. So now we have V increasing, we have Y increasing. All right. So that means the kinetic energy is increasing, the gravitational potential energy is increasing. However, there's no springs. Remember, this is not compressible, so I can't treat it like a spring. That's important because I don't have any spring potential energy. So I'm changing the energy. So that I have a changing energy. What causes changes in energy? Work. Work causes changes in energy. So work equals E final minus E initial. Oops. E final equals E initial. Well, E final is all this stuff over here. So that's the kinetic energy at 2 plus the gravitational potential energy at 2, spring potential energy at 2. There's no spring potential energy. Energy initial is the kinetic energy at 1 plus the gravitational potential energy at 1, I forgot 2, plus the spring potential energy at 1. There's no spring potential energy. So what do I end up with? The work is E final, which is K2 plus UG2 minus the E initial, which is K1 plus UG1. All right, this is getting crowded. I'm going to get a new sheet of paper. Let me write this out again. The amount of work that's being done is K2 minus UG2, oops, plus UG2 minus K1 plus UG1. Here we go. Well, let's plug it in. Work is 1/2 the mass that's being moved times the velocity at 2. Ooh, I know what that is. Plus mg, my final height is y2, minus 1/2 mv1 squared, I know that, plus mg y1, which I know that as well. Yay! Well, I know some of this stuff. I'm kind of stuck. I need to work on this work. Work is force times distance. How far does it move? Let's go back and look at this little slice right here. this little slice right here. All right. So, well, let's look at the forces on it. Well, there's a pressure pushing down over on this side. Pressure 1 is on this side. Pressure 2 is on that side. We're generalizing here. So now, pressure 2 is pushing back that way. Pressure 1 is pushing up that way. I think I need to look at a free body diagram. These forces that are on there. So, free body diagram looks like this. P1, wait, I'm going to call it P, I'm going to call it F1 and F2. Well, F1 is pushing up that way. I'm going to make this way positive. So, F1 is pushing that way. F2 is pushing that way. The sum of these forces is what I'm looking for. I want to find out what F to put in there. So I'm going to have F1 minus F2. I'm running out of space here. So this is going to equal F1 minus F2 delta X. But F1 is going to be pressure 1 times area minus pressure 2 times the area. Delta X, we'll pull that A out, P1 minus P2 times A delta X. Well, my area is just going to be this area times my delta X, which is right there. And area times the delta X is a volume. This is my change in pressure across there. So that's how much work is being done. Let's plug this into there. So now I end up with P1 minus P2 times volume equals 1/2 mv2 squared plus mg y2. Oh, we can almost read it. Y2 minus 1/2 mv1 squared plus mgy. All right. Let's divide both these sides by volume. Alright, I'm going to switch colors so you can read it a little bit better. Mass over volume, mass over volume, mass over volume, mass over volume. We know that as a different letter. Alright, let's plug that in and go from there. What do I end up with? I end up with P1 minus P2 equals 1/2 rho V2 squared plus rho GY2 minus 1/2 rho V1 squared plus rho GY1. Alright. I'm going to add this to both sides, add this to both sides. Alright, we'll end up with P1 plus 1/2 rho V1 squared plus rho GY1 equals P2 plus 1/2 rho V2 squared plus rho GY2. What does this mean? As I change the fluid, as the fluid changes states through this pipe, these three terms that are on that chunk of fluid, as I rotate them around, they stay the same. This is Bernoulli's equation.